Hi, welcome to this video on electronegativity and bond polarity. So electronegativity, we just start with a definition. This is the ability of an atom to withdraw electron mass in a covalent bond. So, we'll take a very quick example of this. Let's just do two imaginary elements, X and Y, that are covalently bonded to each other. So the electrons, one from X and one from Y, sit, we assume, somewhere in the middle. And that's then where electronegativity comes in. Because although we've got two electrons there, sat quite happily in the middle, being pulled by X and pulled by Y, they don't pull equally, these electrons. They're both attracted to them because they've both got nucleuses full of protons, and they're trying to pull the electrons towards them. Now, the more electronegative something is, the better it can pull. So let's say X is more electronegative than Y. These electrons are going to shift and move closer to X because it's more electronegative, and it can withdraw the electron mass, just the electrons, to itself. It can pull them closer. So X in this case does it better than Y, so electrons move over, and that's electronegativity. Now there is the Pauling scale, and this is where every single atom on the periodic table has its own electronegativity score. So I've just chosen a few here. Now the key thing I'm going to look for in this, when we covalently bond, is it equal or greater to 0.5? So the difference even. So if the difference is greater, then we get what's called polar bond. So that means one of the atoms is so much more electronegative than the other, it forms a polar bond. And I'll go into what that is in just a sec. So let's take hydrogen and carbon first of all. So 2.1 and 2.5. Carbon does draw the electrons close to it. So the electrons might sit slightly closer to the carbon, but not enough for what we call a polar bond. Instead, if we take hydrogen and nitrogen, and we have 2.1 and 3.0, now the difference is at 0.9, much greater. The electrons move so close to the nitrogen, they actually affect its overall charge, and it becomes slightly negative. Just to show that it's slightly and not a full negative charge, we use the delta minus symbol. So delta, just drawn all sorts of weird different ways. You might see it like this. I tend to draw it like that. Lots of different ways to draw the delta. It doesn't really matter too much, but because this has got slightly negative, the hydrogen balances it out and becomes slightly positive. So this nitrogen, we say, is electron rich. This hydrogen is now electron deficient. That delta plus says it's become electron deficient. And that's polar bonds. And we can do this with lots of different ones and have a look. So we can go with oxygen and hydrogen. And we've got 3.5 there, 2.1 there. So the electrons move closer to the oxygen. Oxygen becomes delta negative, hydrogen becomes delta positive. Into HCl, hydrochloric acid. Electrons difference of 0.9, so very similar to the nitrogen. We're going to get delta minus there, delta positive there. Hydrogen tends to become delta positive because it's got what is a relatively low value. So that's electron negativity, and what we get is these things. When we get a delta minus and a delta positive, we've got two sides to them, two poles. These are now polar bonds, we call these. So this is a polar bond. And we can, from this, get polar molecules. So the classic case being water is a polar molecule. We have a look at water. We've got our O attracted to two H's. So in this covalent bond, the electrons are going to move closer to the oxygen. Always good to put the lone pairs on the oxygen. So oxygen becomes delta minus. Each of the hydrogens becomes delta plus. So oxygen's pulling on both these electrons exactly the same. It doesn't get halved because there's two bonds. Now, there is a slight exception. We will say this now is a polar molecule. Not all molecules with polar bonds become polar molecules. Because this is uneven, that's absolutely fine. We've got kind of a positive side and a negative side. In something, let's say, carbon and fluorine, nice and tetrahedral, but all even, all the way around. Fluorine, most electronegative atom is 4.0. So fluorine, delta minus, we've got delta minus, delta minus, delta minus. So we've got lots of polar bonds, 4 polar bonds, but they're all pulling equally, all creating dipoles in the same direction, so they cancel out the overall polarity. So this is not a polar molecule because it's all even. Water, because it's uneven, hydrogens are both to one side, they won't be. If we take another example, one that isn't, carbon and oxygen, so big electronegativity difference, so we do get polar bonds here, but because they're pulling on either side, it's not a polar molecule. So not a polar molecule. And that is electronegativity and bond polarity.